Hey, good evening, everyone. Today we'll start with the remaining parts of 3.10. There's two sections. One's titled differentials. They also put linear approximations, so I'll add that to this. Differentials and linear approximations. All right. And 3.11 is a whole new set of functions called hyperbolic functions. We won't go in deep into 3.11. I don't want you to think that's a section we spend like 2 hours of class on one section, but it is part of the course curriculum. One of the sections, the math department always debates whether to keep it in there or not, or remove it, but hyperbolic functions will appear in a differential equations course. They appear from time to time in the calculus course. So they allot just like a half hour for it. They're like, oh, let's just do like a half hour instruction on it. So, although we'll hit a light, you'll get an idea of what they're all about. And then 4.1, I think we can get into maximum today. I'm gonna draw an image. I got most of it drawn here on page 253. This is in 3.10. Now when you all see this tangent line at some point x, there's a tangent line at the point x. And I picked another point on the curve, just like they did in this image. And this is figure number 5. But it's the best picture in that whole section. I just picked another point here, just like they did. And we can call this x plus change in x, right? All right. So what's going on here is from here to here, stop. Can I call that change in x?
Yeah.
That's change in x, right? So, we'll finish the picture together. Like, all right, so from there to there, I can call that distance change in x, true?
Mm-hmm.
Now I'm going to go vertically from here to here, and that point's on the curve. So can I call that change in y?
Mm-hmm.
Good. Change in y. And if I did compute change in y over change in x, actually, I would get the slope of a secant line right there, right?
Yep.
Yeah, that's change in x and change in y and change in x. Now, we've been talking about derivatives, like dy dx, derivative of y with respect to x. Well, that's a ratio, isn't it?
Mm-hmm.
So I want to show you where is that in this image. First of all, you could say change in x is equal to dx. So both of those would have the same distance. But just like they did in this image, dy would go from here all the way up to there. All right, so I'll just kind of go like this. Look, from here, I'll go all the way out here. From this location to this location, that's dy. And dy or dx gives us what? Slope of, yep, slope of the tangent, the curve.
Why dy is going so up?
Because of that ratio, we can think of this as a ratio.
Uh-huh.
Dy over dx would give me the ratio, the slope of this tangent. Does that make sense?
Oh, because
Yeah.
the slope is same. Okay, got
Yep,
it.
that's right.
Okay, got it.
But you all can tell, change in y is not equal to dy, is it?
Yeah.
But they're close to each other in this image, aren't they? So it's just something, if you want to make a note of that, you go, this was dy, change in y only went from here to here. But they're close to each other. They're close to each other in this image here. Dx does equal change in x. So of all the images they put in 3.10, that was my favorite by author James Stewart. Right, I like that one. And I'll leave that up there. But what we're saying is, okay, well, we know this. Everyone agree?
Mm-hmm.
But what if you looked at just dy separately? It's f prime of x,
Times.
put that over here,
Mhm.
yeah? And there's a name for this. So what's that alone? This is called the differential. It actually has a name, so you can call it the differential. dy is the differential. And sometimes you like to see it. That's why I like this image. You go, can I see it, mathematics? Can I just get an image of what you're talking about?
So,
The differential.
so differential is not the same as change in y.
That's right. But how about this? Differential is not the same as change in y. But we can tell they're very close to each other.
Yeah.
If, as long as the change in x is not too far.
Yeah.
You all like that? And feel free to write something about that if you want to just jot that down. I think this image kind of tells a story. As long as change in x, you don't go too far away. If I went way far away, do you agree? I think the dy and the change in y would have dramatically changed in terms of their difference. Do you agree?
Mhm.
But as long as change in x is small, you didn't go too far, you just went, stopped. Then we can tell that change in y and dy will both be close to each other. It's almost like I could say this. Change in y is roughly approximate to this, as long as change in x is what?
Small.
And I can put like very small just to emphasize it. So those would be, very close to each other. So these would be very close to each other. They're true as long as change in x is really tight. Can you see that? So if you shrunk change in x, look at that. What if change in x was like, whoop? Well then, there's change in y and there's dy. And wouldn't they be almost on top of each other? Cool?
This is kind of like the delta epsilon function.
Exactly right. That's it. So that's my favorite image. So if you hear this word differential, you can almost make an image of it. You go, okay, I got it. Is delta y, is dy equal to change y? Nope, it isn't. It is not. It's called the differential. We know it comes out when we see this representation. We can write it as f prime of x times what? Dx, right? We can write it that way. And that's what you have. Well, we're going to use this, everyone, to do what's called a linear approximation. But that's that. I like to show you that. So you get an image of it. dy, you can call it a differential.
Now, f of x is the that curve, right? Yeah, sorry.
That's right. That's right. Everyone, let me put that here. This curve was f of x. That curve right there, this curve going like this, was f of x. That was just the tangent line drawn at x.
Yeah.
Best picture out of 3.0. Helps us make sense of, differential. What is it? I like this. The author did a little blip on application of physics on page 252. And he wrote this. All right? He goes, add 0. He's talking about physics. So everyone, add 0. That means that x equals 0. And he wrote this. And you go, what? He goes, add 0. Sine of x is close to that. And he's talking about a linearization. You might be like, what are you talking about? We'll talk about a linearization here in a second. I'm going to draw a straight line. Linearization is a linear approximation. So another word for linear approximation is a linearization. Well, what's that? It's simply just drawing a tangent line. So linear approximation, linearization. Can you come up with one other term? How about tangent line approximation? Tangent line approximation. All right. Well, what the heck is this about? Well, to understand this, they said applications of physics. Why is sine of x near x when x is near what? And x is near what value?
0.
0. Because what's the sine curve doing at 0?
0.
It's like this. So let's say, and then the sine curve, doesn't it take off like this?
Uh-huh.
But if you're right near here, and someone's trying to find out like sine of 0.2 or sine of 0.1, notice I'm using x values very close to what?
0.
0. And someone doesn't have a calculator or table of sine ratios or anything like that,
0.
they could use the tangent line here. And you go, what's the tangent line drawn to the sine curve right there? It's the tangent line y equals x.
Yep.
And they could use this to make approximations. This equation right here, y equals x. To get approximately, what's the sine of 0.1? Sine of 0.01. You go, oh, well then sine of 0.01 could be roughly 0.01.
Mhm.
Cool. But we're going to do this with the square root function. So don't worry about that, but that was on page 252. So let me erase this. This is what I'm talking about. We'll make sense of this. We're gonna do a tangent approximation, or a tangent line approximation, or a linear approximation. Or in other words, we're gonna find what's called a linearization. Now here's the problem. We're gonna use the square root of x function, okay? Think Salmon's going? Take notes from? Oh, thanks. All right, Owen. You and I are going to find the linearization. Okay, I'll put in parentheses linear approximation. We can call it L of x. We're in as a function, L of x. Of the function f of x equal to the square root of x. All right, now I gotta pick a point. I gotta pick a point. You know, and I'm not gonna pick 32. I'm not gonna pick 43. I'm gonna think of something that's just a perfect square. What are some perfect squares?
64.
I like 64. What's another one?
81.
81's great. 16. I'm gonna pick one of these. Okay? I'm gonna pick one of these where we got the what? Just some perfect square. 100, 81, 64, 16, 25. Now we do this so we can get an idea of what these linear approximations are all about. So, all right. You know what I'm gonna use? I think I'll use 9. Okay? All right. I don't know why the author likes to use the letter A. But when A is x, so if you want to say x equal to 9, go right ahead. I wrote it A equal to 9. Because I noticed the author writes that in the book. I'm going to use A equals 9. It's at the x value 9. So we're going to find a linearization at A equal to 9 or x equal to 9, A being some x value. Okay. And we'll do part A, part B. Let's make this part A, and then part B, we'll use this linearization we find to make an estimate.